Welcome to this video lecture. This is Mark Scythian. The date today is August 5th, 2018. In this video lecture, we're going to cover applied calculus mathematical modeling for calculating unknown rates of change based on known rates of change over the function of time. So here we have an applied calculus mathematical modeling scenario, drug dosage, metabolic rate of change. Assume that a patient receives a certain drug with an initial dosage of 7.45 milligrams per deciliter blood density of the drug at 12 a.m. and then at 1:15 a.m. or 75 minutes thereafter, the patient's blood is tested for the same drug and the dosage level is recorded at 6.13 milligrams per deciliter blood density. This drug specifications list a minimum effective drug dosage of 3.91 milligrams per deciliter blood density. Calculate the time for which this particular patient's bloodstream will reach the minimum effective dosage of this given drug. Also, calculate how long after the initial dose the drug level will reach 0 milligrams per deciliter blood density. So we must first establish the finite time limits, what we do know. So t is equal to 0 and t is equal to 75. T can be substituted for x since time is always on the x-axis. So our initial dosage time, t equals 0, 75 minutes after initial dosage, or 1:15 a.m. we have t is equal to 75. Since this is obviously a decay factor, not a growth factor, we can take the ratio, so the factor is less than 1, 6.13 over 7.45, and that would be equal to some variable to the 75th power, we'll call it a, to the 75th power. So if we want to solve for a, we have to get the 75th root. So if this was a to the 1/2 power, that would be square root. To solve for it, we would have to get that inverse, a square. And in this case, we get 75 of a to the 75th power. We need to get the 75th root, the inverse of it. So we just take 6.13, divide it by 7.45, whatever that equals. Take that to the exponent of 1/75th. And then you have your decay factor established at 0.997, 403, 1206. For precision's sake, not accuracy, but precision, use the untruncated full factor. Try not to truncate it, especially with drug calculations, as to keep the tolerances as close and tight as possible. We can get all the 1 or 2 decimal places rounded on the final answer. So now we model this into a power function. A, not this a, but it's written a times b, or a parentheses b to the t power. So this a represents the initial value, 7.45, parentheses b is the growth or decay factor, and then to the t power, and this implies within the known time limits. So you could put any value for t from 0 to 75 and calculate what the drug level was in the blood between those time limits of 0 to 75 minutes. But after 75, you would not get an accurate answer because the rates of change are fluctuating. This is a non-continuous function. We can only use this for what we do know. The only way we can find out what we don't know is from a continuous function, exponential modeling. So we need to calculate what we do know first. So to check it, to make sure this was done correctly, we can enter in the decay factor times the initial value, actually the decay factor to the 75th power, then times the initial value of 7.45, and we get this value here, which is exactly where it is at 75 minutes. So this was done correctly. So check that work, make sure the equation is set up properly. So now we have to convert that into this e to the kt power format to get it continuous. So e, look for the e on your calculator, exponential, and then the natural log, the ln, not the log 10, not the base 10, but ln, natural log. So you take the natural log of the growth or decay factor, and then you'll get the constant. Then you set it up again also with the initial value e to the constant times t power. Should be in the power up there, like exponent. So it would be e to the kt power. So the k, we got it from the logarithm of the growth or decay factor, then times t. Now we can enter in a value greater than 75 minutes to calculate the continuous metabolic function. Now we're going to get correct answers into the unknown. So the above is the unique mathematical equation representing the given patient's metabolic decay rate for a given drug right here. So, but we already know what the drug level will be for minimum effective dosage, but we don't know when, the time. Past 75 minutes using the power function, we don't know it. This would not be correct. But converting it into a continuous function using this method of natural log of the growth or decay factor and then set it up to e to the kt power, we now have a continuous function past the anything greater than 75. We would be able to use this 75 minutes afterwards. And since the dosage level is recorded at 6.13 at 75 minutes, obviously it's somewhere after 75 minutes it will reach 3.91. So we can't use a finite non-continuous function, a power function. We need to use the exponential modeling of continuous function, which is tailored from the finite values, but it does equate the rates of change in accordance to the established metabolic mathematical modeling for the given patient. So we know the y output is 3.91, so we don't know when. So using the rules of mathematics, you would just divide these out, because you're trying to cancel, trying to get the e isolated. So you divide both sides by 7.45, you get this value, but you're still left with this e to the kt power. So in order to get rid of that e, if you multiply natural log times e, you get 1. So therefore, if you took the natural log of both sides, you would get the natural log of this value here. You'd cancel the e out, and then you'd be left with a nice, neat algebraic expression that can be easily solved. So then you take the natural log of this value, this ratio here, you get this value to equal this expression. Solve for t, just divide both sides by this value here, so you get t. So you're left with this value divided into this value to equal t. So 248 minutes. We can round that up a little bit. That will not lead to incorrect answer. So 248 minutes after the initial dose, which is also 4 hours and 8 minutes after 12 a.m. on a certain date. So at 4:08 a.m. is when dosage level will reach its minimum of 3.91 milligrams per deciliter for the given patient's unique continuous metabolic rate. So we have the proof here where t is equal to 248. Now the next question is, when will the drug completely metabolize out of the person's system? And if you took the graph of this equation right here, y is equal to this equation, put it in your graphing calculator, you'll get a curve that comes down, drops, but you'll notice that if you zoom in, this will continue onward, and it looks as if it's reaching 0, but it's not. It's actually hovering right over the 0, going on and on and on, and you could take your time and eventually find the point where it reaches 0 and say, okay, that's when the drug's all gone. You'll notice that the less and less of the drug, it takes longer and longer to metabolize out. Of course, anything below 3.91 is not effective, but perhaps there's some drug testing for something else perhaps it might create a false positive for some other test. So one might not want to have any of the drug left. So the good question to ask is, when will it go to 0? Well, there's one problem, is that if we try to equate this equation to 0, we cannot solve it. It's undefined. So we use the concept of a limit approaching 0. As for when drug will metabolize to 0 milligrams per deciliter, this can quickly be calculated by establishing the given function up to approaching 0. However, calculating the function above to absolute 0 will result in an undefined function that cannot be solved. So equating 0 to equal a value very close to 0, such as 1/1 millionth, will suffice as 0 milligrams per deciliter, since mathematically this is still not 0, but in practical applications it is, because it would be below any traceability, and it would be literally or practically 0, but technically not. So you actually get away with solving an accurate equation with a limit approaching 0, which would be something very close to it. So then you can take this continuous function mathematical equation representing the given patient's unique metabolic rate and equal it to a value very, very, very close to 0. Now it's all about just solving it like we did previously, then getting rid of the exponential by multiplying the log times both sides. So you're left with this algebraic expression to solve it, and that would equal when you divide these out right here, you get 6,085.5 minutes, or 101 hours 25 minutes, 4 days 5.3 hours. Based on the given patient's unique metabolic rate as mathematically modeled, the drug will reach a dosage level of 0 milligrams per deciliter exactly 4 days and 5.3 hours after initial dose, provided no further doses are administered. This means that if initial drug dosage was administered on, let's say, July 1st, 2018 at 12 a.m. of 7.45 milligrams per deciliter, it will reach 0 milligrams per deciliter dosage levels in patient's bloodstream by July 5th, 2018 at 5:18 a.m., provided no further dosages are administered after the initial dose. Now, of course, this data could be programmed into medical equipment so that it monitors in relationship to a mathematical model, and then it's saved into its memory, and then it's the patient's file or their unique metabolic rate is mathematically quantified. So, of course, you would use the calculus application, and using the exponential modeling is actually a accurate and fast way to do so. You could use derivatives, rates of change. You could use how much blood flow, integral, volumetrics. You could do that too. But this is actually the fastest way to get the same result as well. So keep in mind power and exponential modeling in calculus, because it's very, very valuable to practical applications. And this could be for population modeling, economics, rates of change in any system, in any science, in any technology. So calculus is very universal to just about anything that exists in matter and energy, moving or stationary, or both. So universal language of the universe to describe it is mathematics, and especially in the calculus and the differential equations level. Thanks for watching this video. Subscribe for access to more videos like this one, and have a great day.